Okay, so as I said before, these next two lessons are about specific types of torque problems. So this one's going to look at what's called the beam problem, and the next one's going to look at what's called the ladder problem. So these are the kinds of problems that you're going to look at. And so what we want to do is be able to, first of all, we want to get comfortable drawing the free body diagrams for these, and then we're going to want to look at how we go about solving these things. So this is a rope. So this is obviously a tension. That should be a straight line, not a curvy monster. That's okay. So we've got tension there. We've got a force of gravity acting down at the end. We're going to have a force of gravity acting from the middle of the beam. We can see that this beam, it's uniform. It looks exactly the same all the way through it. So force of gravity is going to be acting at the center. Now the question is, though, what is happening here? There's a hinge here. And now the question is, what's the purpose of that hinge? First of all, one of the things it's doing, if we look at what's happening here, this tension, again, this wouldn't be part of the free body diagram, but just to help you out here a little bit, I'm going to draw in the components of tension. I'll call this Ty, we'll call this Tx. Tx is pulling backwards here. And so, because this thing is in static equilibrium, there must be a force acting to the right. The only place for that to happen for this beam is right here. So there's got to be a force acting to the right. That's actually a normal force off the wall. And now, two more pieces here. We've got tension acting up at this. There's a component of tension holding this end of the thing up. But there's forces acting down here and here. So then the ultimate question is, well, what's going on here? Either there's going to be a force up, or this thing's going to be pulling this thing down. And that's going to likely depend on combinations of tensions and like what different forces are acting here. But what is most likely happening is that this guy, is that there's an applied force upwards from the hinge, so that this plus the upward force from the torque is balancing these two downward guys here. Likewise, this thing here, there's going to be an FG downwards here, there's going to be an FG downwards here. There's going to be a tension this way. But then what the heck is going on right there? Again, as usual, likely what's going to be happening here is that there's going to be a force outwards here, an Fn, and then there's going to be an Fa upwards there. But these guys are all just components. Fa and Fn are just components of what we were going to call here. I'm just going to draw it in here. I'm going to call this F hinge, or the force acting from the hinge on the beam. So this types of problems are things like drawbridges or masts on a ship, again, assuming that there's sails and stuff involved, or in building cranes, we get stuff that looks like this. So you can set this up one of two ways, where you can use the perpendicular components of the forces, or where they can use what's called distance components. Again, that's not a technique I've taught you. I'm not going to. It's not going to be super useful or necessary to us at this point. If it becomes necessary for you to learn it, your university profs will teach it to you next year. But by then, they're going to be approaching torque in an entirely different way anyway. So you'll learn a whole bunch of techniques next year. So for this particular problem, we want to find cord tension and the force exerted by the hinge on the beam. So what's actually going on here? So the way that the book outlines the solution for us, again, this thing's not moving, and so the implication here is that this thing is in equilibrium. If this thing is in equilibrium, well, we've got a few things. We know that the torques clockwise are equal to the torques counterclockwise. That's going to give us this first guy here. We know that my forces up have to equal my forces down, and my forces left are going to have to equal my forces right, which is going to give us this guy down there. So let's draw our free body diagram. And I'm just going to put as much information in there right away as I can. So there's a load on the end. So there's going to be a force of gravity here We're told the mass is 0.7, so I'm just going to go ahead and do the calculation. 0.7 times 9.8 is 6.86 newtons, so that's the force acting downwards there. There's a force in the middle, from the middle of the beam due to gravity. Fg, we know the beam has a mass of 0.22 kilos, so 0.22 times 9.8 is 2.156 newtons. What else have we got? We know there's a force on the hinge. So there's going to be a normal force acting out and a force acting up, likely. We're going to find those later. We got tension here. But that hinge is going to act as a nice little pivot here. So because it's acting as a nice little pivot, I'm going to not worry about the hinge force at this point. We're going to use torques to find the rest of the information here that we need. So I'm going to draw on the components now of tension. That's going to be necessary for us. Call this Ty, we'll call this Tx. If this is 30 degrees, then this here is 60 degrees, and components always meet at a right angle. So we can say that Ty is just going to be T cos 60, and Tx is T sine 60. So now we've got to start calculating things. We're going to use the torques to figure out what this tension is, and then we can use the tension to figure out Tx and Ty. Because we're going to need Tx and Ty to figure out using my upward forces and my downward forces, my left forces, and my right forces to figure out what this hinge is doing. So let's do it. Torques clockwise equal torques counterclockwise. So I'm going to have the torque from the load. I'm going to have the gravity of the torque from the force of gravity on the beam, and I'm going to have the torque from the tension force here. So these two, if these were the only ones acting, these two would pull this thing down. So these are going to be my clockwise torques here. So I'm going to have the Fg of the load. I'm not going to put any of the times R plus Fg beam. I'll call that RL times RB, and that's going to equal, well, it's the perpendicular, torque is perpendicular, or we could use, so we could use, again, I'll put this in here, torque equals FR, or torque equals, so F perpendicular R, or it's equal to FR sine theta, depending on what's going on in there, but we're just going to use, I've already made it already, so let's just use the perpendicular one here. So we're going to use Ty times R, I'll say T for tension, so now let's fill it in. Fg from the load is 6.86. The distance from the pivot to the load is the length of the beam, so that's 0.82. Plus Fg from the beam, which is 2.156 times the, no, sorry, that bracket's going the wrong way, times the distance from the pivot to the middle of the beam, which is going to half the beam length, which is 0.41. And that's going to equal T cos 60 times the distance from the pivot to the beam, or to where the, sorry, the distance from the pivot to where the tension acts on the beam, which is the very end. So that's just going to be the length of the beam, which is 0.820. So we can solve all of the only unknown here is T. So we can figure out that our tension force is going to be 6.86 times 0.82 plus 2.156 times 0.4141 divided by cos 60 divided by 0.82. I got a tension force here of 15.876 newtons. So I can go now and I can find Tx and Ty. Ty is going to be that times cos 60, which I got 7.86 938, and then 15.876 times sine 60 is going to be 13.746 newtons. Found my tension, and I found my components of tension. So now, because we found tension in these components, we're going to figure out what this hinge force is here. So I'm going to operate on the assumption that this hinge has a force acting this way. I'll call this the Fx of the hinge, and I'm going to operate under the assumption that this guy is Fy. If this ends up being negative, then we know, if the force y here ends up being negative, we know that my assumption is incorrect and the force is actually acting downwards. But we'll see how this turns out. So I've got F up equals F down. I'm going to set up the other ones over here. F left equals my forces right. So my upward forces are Ty, Fy. My downward forces are the two Fgs. So I'm going to have Ty plus Fy is going to equal Fg load plus Fg beam. Ty is 7.938 plus Fy equals Fg load, which is 2.156 plus the beam. Oh, no, I got them backwards. Oh, that's that guy. This is this guy. And then Fg load is 6.86. So we're going to find here that Fy is 1.08 newtons. It's positive, so I have drawn this correctly. And then F left, there's only one force acting left. That's Fx from the hinge. No, I lied. That's Tx from the tension here. And there's only one force acting to the right. That is Fx from the hinge. So I got to rewrite this. This is going to be Tx, and this is going to be Fx. We already know what Tx is. That's 13.746, and that's just going to equal Fx, because there's only two forces, and so they must equal each other out. So what that does for us is it gives us a picture of what's happening here at the hinge. The hinge here is pushing to the right with a force of 13.746 newtons, and it's pushing upwards with a force of 1.08 newtons. Just going to zoom in now up here. So what we're going to do is we're going to figure out what the hinge force is. What this means, if it's got a right component and an upwards component, what it means is it's actually pushing up this way here. So this is going to be my F hinge. So that's my F hinge. There's a right component and there's an upward component. The right component is 13.746. The upward component is 1.08. Obviously that is not drawn to scale, but these are components. They meet at right angles. Scale is not nearly as important as getting the gist of the picture. So I want to figure out what the force of the hinge is in polar coordinates. So I'm going to use Pythagoras. 1.08 squared. 1.08 squared plus 13.746 squared. Square root that answer. And I'm going to get that F hinge is 13.8 newtons at an angle of, it's just going to be the tan inverse of that of 1.08 over 13.746. Tan inverse 1.08 over 13.746 at an angle of 4.5 degrees. And now we can't use north, south, east, and west, because if you imagine how this is hanging, it's hanging in three-dimensional space. This is up and down. So this is 4.5 degrees is going to be above the horizontal, or above the beam. There's a couple different ways you can explain that, but this is the force from the hinge there, the force exerted by the hinge. So we're done. I'll zoom out so you can see the entirety of the question. We're going to do one more example. It's going to be it's going to be a little bit more gross, and then you guys can take a look at some of the questions on your own. So here we go. This guy here. There's a little bit going on. Okay, here we go. Last example for this this lesson. So when the beam is not horizontal, the problem becomes a little bit more complex since we need to consider one set of components for the torque equation and a different set of components for the force equations. And I'll show you what that means now. So, yeah, here we go. So first thing, let's draw the free body diagram. We have the force from the load acting down here. We're told that this is an 8 kilogram load, so the force of gravity here is going to be 78.4 newtons, 8 times 9.8. There's going to be a downward force here. Fg is going to equal 117.6 newtons, because we are told that the beam is 12 kilos, so 12 times 9.8 is 117.6. And the tension, oh, we want the tension, so here's the tension. So the reason that this question is so gross is because for the torque, so what we want are the perpendicular components. So I want the perpendicular component of the tension. I'm going to want the perpendicular component of gravity. I'm going to want the perpendicular component of the load. But then when we go and look at forces up and forces down, I want the component of my tension this way, not that way. And so we've got to be, again, depending on which expression you want to use for torque, we've got to be really careful about how we draw this thing. Or, again, the trade-off is the math gets a little bit more complex. We can use a different set of equations for the torques to make that a little bit easier as well. Because remember, torque was equal to F perpendicular times R, or torque was equal to my force times the distance from the pivot times the sine of the angle between the object and the force acting. And so for this particular question, I would like to use this expression just to make my drawing look a little bit cleaner. My pivot is here. And then we're going to figure out what the hinge force is, but we're going to do that later. So first, I want to look at the torques. I want my counterclockwise torques equaling my clockwise torques equaling my counterclockwise torques. I've got this angle here. I'm going to use this expression: torque equals my force times the distance from the pivot to the sine times the sine of the angle between them. So I need these angles here and here. Well, if this is 28 degrees, if this is straight down, this will meet at a 90. So this angle right in there is just 90 minus 28, which is going to be 62 degrees. So that's 62 degrees. This is also 62 degrees. So I'm going to get FG beam times R beam times the sine of 62 plus FG load R load sine of 62 is going to equal my tension times R tension times the sine of 55. I'm going to put some values in here. It's going to shrink this down a little bit here. So FG beam is 117.6 times R beam. We're told this is a 12 meter beam. Force of gravity acts in the middle of a uniform beam, so that's 6 meters. Do I have the value right there? No. Oh, bad. That's a 7 meter beam, so that's 3.5. It's a 12 kilogram beam. So anyway, sine of 62 plus FG load is 78.4 times R load is the distance from the pivot to the where the load is on the beam, so at the end, times the sine of 62, and that's going to equal T. Now the distance of the tension, so this is 6 meters. Sorry, this is a 7 meter beam. This is 1.1. So my tension is a distance of 5.9 meters from the pivot times the sine of 55. Now this is all just numbers, and so we can solve for T. If we do that, you should find that T, I'll let you do that calculation. I've done it already. I found that the tension is 175.4 newtons. So by using this expression, we were able to keep the diagram really quite clean. Now the only things that I'm going to draw in here, I'm going to draw in my vertical and horizontal components of tension. I'm going to call this Ty and Tx. My diagram is still really quite clean because these guys are already acting up and down. So now when I want to go through and now I found my hinge force, it's going to be a lot neater. So again, this thing is still not moving. Static equilibrium, and so we've got my forces up equal my forces down, and my forces left equal my forces right. So let's fill this thing in here. My upward forces, I'm going to operate under the assumption that there's two of them. I'm going to have Fy from the hinge, and I'm going to have Fx from the hinge, and then I've got Ty and Tx. So my force is up. I've got Fy up. I've got Ty up, so Fy plus Ty. And my force is down. I've got these two loads. So I'm going to have Fg beam plus Fg load. So I'm going to get Fy plus, now Ty, I got to be careful here because I need a... Oh yes, this is good. This is gross. So I need to figure out what these angles are. I need, yes, right. So, if we were in class, I would say, okay, who sees what and what do you think about what's going on here? But you're not there, so I'm going to show you what I see and how I would approach this. So, I'm going to add here a horizontal line, as close to horizontal as I can get it, right into there. What that does, this creates a Z here. It's going to create for us alternate interior angles, so a concept that you should have seen in math before. So what that means is that because we've got these two lines are parallel and this line bisects, or going across them like that, this angle here and this angle here are equal. So if this is 28 degrees, then this guy here is also going to be 28 degrees. If this whole angle is 55 and this little piece is 28, that's going to make this 55 minus 28, which makes this 27. So then we can see that there's another Z here, so I've got a Tx, another Z, so another alternate interior angle, which makes this guy here 27 degrees as well. So that's that 27 degrees that I'm going to use here for Tx and Ty. So Ty is going to be T sine 27. And that's going to equal Fg beam plus Fg load, so 117.6 plus 78.4, so Fy plus, I found T before, so that's going to be 175.4 times sine of 27 equals 117.6 plus 78.4. It's going to give us an Fy acting from the hinge, sorry, I'll slide that up a little bit here, of 116.34. And then my forces left equals forces right. My leftward force is Tx. My rightward force is Fx. So my Tx is just going to be 175.4 cos 27 from this triangle up here equals Fx. And so I'm going to get this as 156.3 equals Fx. So that gives me Fx here on the hinge of 156.3, and it gives me an Fy of 116.34. So I can figure out what the force is from my hinge. I'm going to zoom this in. We're going to get 156 this way. Point, what did I say? 3. And then a force upwards here of 116.34. So this is F hinge. I'm going to use Pythagoras to figure out that this is 195 newtons. And I'm going to use tangent to figure out that angle there, so the tan inverse of this 116.34 divided by 156.3 is 37 degrees. And that's it. So I'll zoom this out so you can see the whole question. I'll show you what this could have looked like alternatively. If we'd done it the other way, it gets a little bit messier. If we use this expression rather, because then we would have had to have gone through and find the perpendicular components here and here for these two loads, and the procedure just gets a little bit more gross. But other than that, that is this question. If you have any questions about any of this lesson, please fire me an email. Whether it's the angles that the angle relationships that I argued, or anything about any other part of this, Newtons. Or if you figure I made a mistake anywhere, please do let me know. But this is the end of lesson 4. So the questions that I want you to take a look at for homework are as follows. I want you to do questions 1 to 3 on this page here. 1 to 3, and then there are some really rocking questions on the next page. I'd like you to try question number 6. 4 and 5 are also great, but I won't make you do them.